It is a pleasure to have today both Zhang as our speaker. I'll do a little bit of a broad introduction in just a minute, but just for logistics. So we need to do the sign-up sheet. So I have to improvise a little bit because I forgot the paper. But so I'll just pass it around, and if you are registered on the course, please remember to sign up here. And so, as I said, it's a pleasure to have both here. Dr. Zhang is an assistant professor of biostatistics in the Vaccine and Infectious Disease Division at the Hodge Cancer Center. He earned PhD in statistics and data science from the Wharton School at the University of Pennsylvania. His research focuses broadly on causal inference and its application in medicine and public health, with recent work centered on vaccine and immune correlate studies. He's a recipient of a Center for AIDS Research New Investigator Award and an NIH NIAID Harlow Grant. So welcome, Bo, and thank you for being here with us.
Cool. Thank you very much, Abel. Yeah, I have to say it has been a while since I see so many people, so that's pretty remarkable. So today I will be sharing with you some of my more or less recent work, things that I found pretty interesting. And yeah, so the theme of the talk will be on how to strengthen an instrumental variable. So here's a roadmap for today's talk. So today's talk have two parts. In the first part, I will talk about how we design and strengthen a continuous instrumental variable. And in the second part, I'll talk about how we actually can also, quote unquote, strengthen a binary instrumental variable. Okay, so the first part of the talk is joint work with Ming. She is a PhD student at UW Biostats, and Zoe, she is now a postdoc at UPenn. So here's a link to the paper. It's in press at JAWS application case study. So I'll start by telling you a story about a particular application. So in a 2010 paper by Ochi et al., they want to study the effect of high-level versus low-level neonatal intensive care unit, NICU, on infants' mortality rate. So here's a brief back. For that particular problem, the treatment that researchers are interested in is this high-level versus low-level NICU. So essentially, it's a better hospital. Okay, it's a better ICU unit. The outcome of interest is infants' 30-day mortality rate. So usually, if you're familiar somewhat with causal inference, so a naive analysis of this treatment on the outcome is typically biased. Typically, you will see a higher mortality rate at better hospitals. And this is because mostly sicker patients are typically sent to those better hospitals. So mathematically, we say there are a lot of emerging confounders that simultaneously affect which hospitals these babies were sent to, and also their mortality rate. In these analyses, what people typically do, ideally, is to find an instrumental variable. And this is a pioneer work by Angers et al. So what people do is, instead of looking at the effect of high-level D, of high-level versus low-level NICU, D on Y, we switch gear and focus on, quote-unquote, the effect of an instrumental variable on the outcome. And roughly speaking, in this particular study, the instrumental variable is access travel time, essentially where this mother and their kids live, whether or not the person, the kid live closer to a high-level hospital or a low-level NICU, okay? And so there are standard IV assumptions, which says that this instrumental variable is not associated with this emerging confounder. You can essentially think of this IV as some sort of a randomizer. It's a lottery, it is an external force. And also this IV directly affects, here we think of it as a causal IV. So this IV directly affects the particular choice of a hospital, high-level versus low-level hospital. And it also eventually the IV does not have any direct effect on infants' mortality rate. So any effect that you see of IV on the outcome is mediated through this choice of hospital. So there are standard approaches. Econometricians pioneer these things. They call it two-stage least squares. This is standard IV analysis tools, often taught in the econometrics classes and also in causal inference class probably. But today I will be focusing on something slightly different. I will be focusing on what is known as a design-based approach to this instrumental variable analysis. The first paper is written by Hideo Imbens and Paul Rosenbaum, 2005. Which I found particularly interesting. So here is a very intuitive setup. So if you just ask a layperson, what would people do if you want to ask them to sort of get a sense of the so-called treatment effect? So a very natural thing is just to compare two very similar mothers, but they have very different access travel time. So I come up with two mothers, one live close to a high-level hospital, one live close to a low-level hospital. I want to systematically compare these mothers and see if their infant mortality rate actually were different. Okay, so this is the intuition. And here, just to be very specific, the access travel time is time to high-level nearest high-level hospital, subtracting time to the nearest low-level hospital. Because in the data set, we do have they do, and we do have essentially those mother zip code, home zip code, so they can actually calculate the distance to the nearest hospitals. So here in this particular setting, a large access travel time, a large IV dose means the mother lives far from a high-level hospital and therefore discouraged from delivering at a high-level hospital. The most important thing here is no one is forced to do anything. They can choose whatever they do, right? So this is the natural experiment, just provides some incentive, encouragement or discouragement for people to actually deliver at a high-level, low-level hospital. You can imagine there are many mothers who live very far from a high-level hospital, but still choose to drive all the way to a high-level hospital. What makes a little bit detailed, but what makes this a particular good idea is because they actually study the preterm babies. So these are the preemies. So they were delivered almost all of a sudden. No one planned a lot for that. So most naturally, people would just drive to whatever the closest hospital that is available, essentially. So these are all preterm babies. Okay, so in that particular paper, it's also a just application case study. They actually consider two study designs. In the first study design, they utilize all data in Pennsylvania across a 10-year period, and they created almost 100,000 pairs of two babies. Okay, one live close, one live far. And in the second design, which is their main point, is they did something pretty controversial, slightly innovative. They tried to strengthen this instrument. So what they did is they only paired two similar mothers whose instrumental variable, whose access travel time were actually far apart. And in this way, they actually throw away half of all the pairs. Okay, so they only create about 50K pairs, but this is a strengthened instrument. You will see momentarily. So here's a very toy example. This is not true, but it's a toy example. Let's say you have four similar mothers, identical mothers. You have four IV doses. Okay, it's 1 to 100, 101. You can pair them however you want, right? Intuitively, it makes sense to pair 1 with 100 and 2 with 101 instead of 1 with 2 and 100 with 101. So that is essentially their intuition. And this is intuition, but I will formalize this later. Okay, but by doing so, they actually discarded half of the data. Okay, so this is what we try our best to reproduce what they have. They report in their paper. It's not precisely what they have, but roughly. Okay, so this is the first design, match 0, about 90K, 91K patients, so, mothers and their kids. So you can see, so these are all the baseline cohorts. If you look at the first two columns, you can see these mothers, more importantly, their kids, they have very similar birth weights, gestational age, the gestational diabetes, whether or not the parity, mother's age, and whether or not it's a Black mother or not, below poverty. They also match on their neighborhood characteristics, which is important, right? Because distance is clearly associated with your neighborhood characteristics. Okay, so they are comparable. And more importantly, if you look at the access travel time, two mothers, one lives like approximately 6 minutes, the other is 21 minutes in terms of their access travel time. So this is quote unquote okay IV. It's not too strong, 6 minutes, 21 minutes. You can imagine you can drive 15 more minutes, right? And the second design, what they did is they throw away half of the people. Within this particular design, you can see you can see these two columns, they're still comparable, okay? Although if you are very curious, they're not the most comparable with the entire study population, but at least internally, they are so quote unquote valid. There is some internal validity. And the good thing about this design is now the access travel time, there is almost more than half an hour difference. And actually, I can tell you this translated to a very large difference in our compliance rate. So we stop there when after we read this paper, we are thinking, so what changed between these two designs? There is a very obvious thing that changed, the cohort changed, right? It's not just the sample size, it's just the design 1, design 2 actually has much fewer Black mothers, for instance, compared to design 1. And actually there's a very very reasonable reason for that, because in Pennsylvania, at least, the Black mothers typically live in Philly, Pittsburgh, live in urban areas. So here is, if you look at the distribution of the IV among these different groups, if you look at those Black mothers, there's essentially no Fox plots, right? So they're all live very close in similar neighborhoods, usually in downtown Philly. And then we're, the Penn have our hospitals typically in those areas. And yeah, this is why it's very difficult to find two Black mothers who are similar, one living very close to a hell of a hospital, one living very far from a hell of a hospital. So as they strengthen this instrument, they essentially throw away these people. Okay. And the second thing that changes the compliance rate, these two groups differ by, as I said, 15 minutes in the first design, more than half an hour in the second design. I will define what I mean by compliance rate later, but it actually increased from 20% to 40%. This is the initial goal. This is what they want to achieve, but they actually achieved that. And in an earlier paper, you can calculate if you just fix the test statistic or to just test the Sharp-Null like a constant treatment effect. You can calculate, you have two designs. You can calculate what is the asymptotic relative efficiency. And I tell you this essentially, it's the asymptotic relative efficiency is roughly the compliance rate, the ratio of compliance rate squared. So if you double the compliance rate, you can save essentially 3/4 of the sample size to achieve roughly the same power. Okay, the third more subtle thing is that not just the compliance rate changed, the so-called complier subgroup also changed. So again, I will define this later. So essentially what people do is in this entire population, there is a subgroup of people. These people are what is referred to by econometricians, economists as compliers. So these are the people, if encouraged, they're going to take the treatment. If discouraged, they are not going to take the treatment, essentially. Okay, so the seminal work on this instrumental variable analysis, which got them like a Nobel Prize, is that they can show the only thing that is non-parametric identified with the instrumental variable is just the effect among the compliers, not among everyone, right? Because you can imagine there are people who never respond to encouragement. You can never say anything about these people, right? They never respond to encouragement. So so here, because we have continuous IV, it's even more subtle than that. So the compliance category, it is defined with respect to IV dose. You have to fix two dose, and then we define what you mean by a complier. So for instance, let's say in this pair, you have a 5-minute person matched a 30-minute person. So a complier is defined with respect to this IV dose, 530. So this is the mother who would attend a low level when this IV is 30, and a high level when IV is 5. So the person actually comply with this encouragement. So in the original paper, again, I'll explain this rigorously later. They studied an estimate called the effect ratio. It's also known as essentially a Ward estimate. So this is the sample average treatment effect among the complier subgroup. Okay, so they can do inference. They actually know what is quote unquote the effect of high level versus low level hospital on infant mortality, but they only know that for this complier subgroup, which is actually a latent subgroup. So if you switch between different designs, this latent complier subgroup would change and the estimates of two designs would differ. So technically, you're not estimating the same thing. So in some sense, it's not meaningful to say, one thing is more like powerful than the other because you are not estimating the same thing. So, and also if you are curious in this result, we say, it's a constant treatment effect, right? Because if the treatment effect is constant, I can talk about their power. But if the estimates change, it's not meaningful to talk about the power. But nevertheless, it is still a pretty interesting idea, at least. So this idea is actually not very specific to their particular problem. In general, people have some criticism about instrumental variable analysis because, your stats, PhD. So what is the usual statistical procedure? So we start with some parameter of interest. You define a priori, right? And then you want to pursue that parameter. But for the instrumental variable analysis, typically, the parameter of interest is not really defined first, right? So here, Angus so here essentially says you only have control over, you just choose to let the light fall wherever it may, and whatever it lights up, you just claim whatever you find is what you're always looking for. Okay. Okay, so what we want to do here is, but this is pretty one-sided. There are people who are proponents of IV analysis, and will tell you at least a lot of times this IV estimates has better internal validity. Then you just then just do some usual non-IV analysis, because usually that thing lacks internal validity. This is not necessarily generalizable. It talks about the treatment effect among subgroup, but at least they believe most of the time it's a valid estimate for these unknown people, but these are some people, right? Okay, so what we want to do is, so we want to ideally, we just tell people what we want to seek after, and we can sort of adjust the brightness of the light, meaning we can strengthen the instrument to the extent possible. Okay, so what we are actually looking for here is just a sample average treatment effect of the treatment on the outcome. Okay, so not the intention to treat, not the comply average treatment effect. What we want to do is we just want to, later we will just essentially we just bound the sample average treatment effect. This is an estimate that is defined irrespective of the instrument. Okay, you can use different instrument, but there is always an actual treatment effect of high level versus low level hospital on the outcome. Okay, instrument is just your tool, right? Its name is already suggesting this. So we want to define and pursue an estimate, define not irrespective of IV and the design. Okay, and then we try to identify it or bound it and estimate it. Okay, so there are a small part first. Back to the three nuances. The first nuance is these two designs, they actually differ in the distribution based on covariates. So at the very least, the first small thing we did is we want an algorithm that when it actually constructs those matched pairs with different IV doses, we want it to also mimic a given population. Okay, so we do not want to just strengthen the IV without paying any attention to the study population. So yeah, this is called template matching. It's well studied for binary exposure. I also wrote a paper myself, but back then it was lacking for continuous exposure. I'm not going to bother you with how we actually did that, but essentially we just, this is the first part. We create an efficient algorithm based on solving a particular optimal matching problem in a non-bipartite graph. So I'll just show you what the result is. So this is the match 2. So I think this is a better compromise between match 0 and match 1. So if you're careful, you could see essentially all the baseline covariates. It is similar to the match 0. It's similar to the entire population. For instance, if you look at the birth weight, a little bit closer, gestational age, pretty close. The proportion of Black mothers, 16%. So it's pretty close to the entire population. That is essentially all mothers in Pennsylvania. And also, it does try the best when strengthening the instrument. So although the difference is not half an hour, now the difference is like 25 minutes, it's still pretty good. So we sort of create like a compromise between match 0 and match 1. And our inference will be done for this match 2. Okay, so for this particular cohort. Of course, again, this is the inference we do are all randomization-based conditional inference. So technically, it's a statement about these 22,000 times 2 mothers. If you want to generalize it to the entire population, that is an additional assumption that you need to make. But my point is it's pretty representative. Okay. Now we roughly define, I'll just define the estimate. So again, so we have created I-match pairs, each consisting of 2 study participants. So here I always use Z tilde to denote this a continuous instrument. And this Dij of Z tilde, this is a binary potential treatment received on the particular IV dose. Okay, so this is essentially saying, so what hospital the person would go to if the person received IV dose Z tilde set to some number. Okay, so in reality, what we actually have as data is this Z tilde IJ OBS. So for each particular person, we only have one observed IV dose. Nevertheless, I can define this potential outcome. I can think what would have happened to this mother if the mother lives like 3 minutes away, 5 minutes away, 30 minutes away. Although in practice, what we observe is Z tilde evaluated at this Z OBS. Okay? So because the design is fixed, in each match pair, we have a minimum of 2 doses. We have a maximum of 2 doses. Again, let's say 5 and 30 minutes. So I just use this, the min and max to denote the minimum and maximum 2 doses. So here I abuse the notation a little bit. I just use the DT and DC because usually people like treat control. This is abuse notation a little bit, but the important thing is we never dichotomize the dose. Okay, so it is defined with respect to the 2 IV doses. So for this person, this DTIJ is the potential treatment received, the potential hospital that the person will go to if the IV dose is set to the maximum of these 2 IV doses in each pair, so 30 minutes. And the other is what happens under 5 minutes. Again, in reality, you only get to observe one of these 2, right? And you need to make inference. This is why, this is the fundamental problem of causal inference. You only observe one, not the other, okay? Not both, my bad, no. Okay, so again, once you fix these 2 IV dose, we can define the usual way of a complier, always taker, never taker, defiers. So they are pretty self-evident. A complier is a person that comply. If encouraged, DT, the person go to a high-level hospital. Discouraged, just go to a low-level hospital. Always taker, doesn't matter, 5 or 30 minutes, always go to the high-level hospital. Never taker, doesn't matter 5 or 30 minutes, always a low-level hospital. Defier, the person essentially defied. The person would take the treatment if discouraged and not take the treatment if encouraged. As routes, usually we make the monotonicity assumption, so we assume there are no defiers. But you can have, as you can see, there must be a lot of always takers. There might be some never takers. Right? But that, again, the key here is everything is defined with respect to IV doses within each pair. So essentially what I'm trying to say is the person has many, many potential outcomes. We only get observed one, and the inference the only thing we can sort of make inference is what happens to this person under 5 and 30, essentially. And then we have a parallel definition. So this is the definition for RT and RC. So this is what is potential clinical outcome, whether the person died or not, the infant died or not, under the 2 IV doses, okay? So again, this is essentially, and the third key definition is the actual treatment effect. So here, I do not intervene on this instrumental variable, on this IV dose. I just intervene and set this person's treatment to 1 or 0. So what happens if I just sent everyone to a high-level hospital? What happens if I sent everyone to a low-level hospital, okay? And that is the actual quote-unquote protocol treatment. And as you can probably see, so the challenge here is this is our ultimate goal of interest. I'm interested in this unit level treatment effect, but the problem is what I can technically do inference. Technically, it's just RT minus RC, which is a unit of intention to treat, and they're not the same, right? Because there are some non-compliance issues, okay? So this is the estimate that Biochidol defined in their JASA paper. What they defined is this lambda. It's an effect ratio. It's essentially the word estimate. So what it says is, let's say for every 100 mothers who are encouraged to go to a high-level hospital, how many deaths this prevented? This is the interpretation of this lambda, okay? For every 100 mothers encouraged is defined vaguely, encouraged to go to a high-level hospital, how many deaths it prevented? This is precisely what this lambda means. And hopefully it's clear, this lambda depends on the IV dose and the study design, because the mothers being encouraged to go to a high-level hospital changes depending on how you wire these mothers, essentially. Okay. On the other hand, you have those sample average treatment effect. This is unequivocal. It's just RD1 minus RD0, average over every single mothers in this design. This kappa does not depend on who is matched to whom. Okay. So arguably, this is something I'm most interested in. Lambda is what they made the inference for. And yeah, so kappa does not depend on the instrument or who is matched to whom. Okay. Okay, so what we did, so it's a usual thing. People actually derive some bound for the sample average treatment effect in the IV literature, not so much for design-based approaches. In superpopulation, for instance, Thomas actually did a lot of work on this topic. So people try, in the case, when we don't actually know much, we can actually still derive a useful bound for the actual sample average treatment effect. So here, this is the simple bound. Let's say you do know the treatment effect is bounded. For binary outcome, it's trivially bounded. And the target, the sample average treatment effect, it can be shown. Again, this is very straightforward. It's upper bounded and lower bounded by these 2 quantities. And if you look closely, this quantity essentially depends on the intention to treat effect, and it also depends on compliance rate. It depends on the effect of IV on the outcome. It also depends on the effect of IV on the treatment received. Okay, so this is easy to verify. The interesting thing is this LB and UB. If you look at the width of this bounds, it's essentially the compliance rate. Okay, so this is, I think, a fair thing to do. So we are not changing the estimand. We're always trying to bound the sample average treatment effect. But just by changing who is paired to whom, I actually can derive potentially a narrower bound for that the same estimand. Okay, you don't have to throw away any person. You can just rewire your person, and the estimand is the same. The bounds will be shorter if you strengthen the instrument. Okay, and at no cost. Okay, at no cost is not, there is a little bit nuance, but it's mostly true. Okay, so the student can derive, then they can derive the valid test for making inference for LB, because this is just you still need to make inference because it involves RTRCD TDC. Right? It involves both potential outcomes for the same person. You cannot observe them, so you need to make inference for them. So we can derive inference for testing those hypotheses, and then by inverting the hypothesis test, you can construct confidence interval one-sided, two-sided for this upper bound and for the lower bound. Okay, so that's the first thing we can do inference. And there's some standard machinery to improve the variance estimators using covariates. And the last thing that we did in the paper is that look at this probability. It says within each pair, so what's the probability that the first person receives, let's say, 5 minutes, and the second person receives 30 minutes? We assume it's a valid IV, so it is randomized, a half and a half. You can tell me you don't think it is a valid IV, which is, there's some truth to it because there's some association maybe between your health status, socioeconomic status, and where you live. Okay, we control for the neighborhood characteristics, but this is still a possibility. So what we do next is we just, instead of randomization, we allow this pi, the treatment IV assignment within each pair to just bound it between these two numbers. And these two numbers are not crazy. There's a reason for that. For instance, if the two IV doses are the same within each pair, then this evaluates to a half, right? If two persons both live 5 minutes, then it is a half and half. There's no bias in the IV assignment. But in general, the larger the IV dose, we allow more deviation, potential deviation from randomization. This is why I said at no cost is not technically true. It's only true for a valid IV. If your instrument is not valid, then strengthening it may actually lead to a larger bias. Okay. And this is also pretty intuitive, right? Because if you do believe IV actually tells you something about the person, it's not a randomizer. Then if you compare two persons that are very different in their IV, they're just very different. So there would be some bias that leak into this thing. Okay, but back to our problem. So we do allow this model, I call it M gamma. It's indexed by gamma because gamma is sort of some sort of a sensitivity parameter. When it's 0, you have randomization. When it's not 0, you don't have randomization. And also when the two IV doses are the same within each pair, you have randomization. And otherwise, you don't have randomization, okay? And the second thing we do is we still want to test the same null hypothesis, but under that relaxed bias randomization model. And again, you can, by constructing some bounding random variables, you can actually construct a valid test. Okay, it's asymptotically valid at level alpha. Okay, I'll show you what happens to this data sets. So we are going to focus on this design number 2, M2. Okay, so here are the results when we apply the method to the design. So here I do make an assumption that the high level NICU does not hurt you. Okay, so the high level NICU may not help you, but it cannot hurt your mortality for every single person, which I think is reasonable. And K1 is like the maximum effect, high level versus low level. That can potentially be, and of course you can assume this to be 0 if you are super conservative. And so here this I plot the lower and upper confidence limit. So the dotted line here is assuming randomization, the solid line here is assuming a bias randomization. So, and yeah, and the good thing about this confidence interval is technically it's a confidence interval. It does contain a sample average treatment effect, 95% at level 0.05, and also it considers the sampling variability. Okay, it considers the non-identifiability of those non-compliers. And also if you use those biased version, and also actually in here, the bias is not because I assume there's some sensitivity analysis. It's actually just because there are ways to actually test if your matching is perfect, if there is any residual bias even after you design the analysis. So this bias randomization also accounts for the essentially imperfect matching during the design process. Okay. Yeah, and still, I think it's fair to say for this entire cohort, this high level versus low level NICU, there is appear to be a positive treatment effect, and not so much on the composite outcome. And we also did some subgroup analysis. So we also focus on, for instance, all the Black mothers. Unfortunately, we don't have sufficient evidence to say there is a treatment effect among Black mothers. Again, this is not saying there's no treatment effect. It's just I don't have evidence for that. Because despite our best efforts strengthening the instrument, the compliance rate among Black mothers is still very low, about 18%. And this is why you see the interval is very wide here. As I said, the width of the interval, this partial identification interval is the proportional to compliance rate, right? So here it is much narrower. Okay. And also another reason is also because the sample size is smaller. So the interval is also wider. Okay. The other thing is here, we also look at the non-Black but high-risk mothers. These are all pre-specified. So for this population, the sample size is not very big, but the compliance rate is very high. It's almost 50%. And for these mothers, these bounds analysis revealed, I think it's safe to say there is a treatment effect among these high-risk non-Black mothers. Okay. So I'll give you a brief summary. So what we found is delivery at high-level hospital was associated with reduced mortality for preterm babies, and the most substantial effects seem to be observed for high-risk non-Black mothers. Strengthening the instrument helps improve the compliance rate, leading to narrower partial identification bounds. And lastly, from our analysis of those Black mothers, if the IV serves only as a weak encouragement for treatment uptake, it yields very limited information about that group. It's not saying there's no effect or anything. It's just if the IV is weak, you just cannot learn much. And I think the take-home message is if you design some future studies, it's also important to think in which study populations your instrument is the strongest, because that might actually is helpful when you later do your subsequent analysis. Okay, and when we are working on this paper, another problem I had is, so yeah, it's a continuous instrument. By changing who is paired to whom, I can strengthen the instrument. But is there anything that can be said for a binary instrument? Which is arguably a most common thing. Usually people do binary IV. So this is joint work with Ray. He is also a PhD student at biostats, Oliver Dirks, and Yingqi, my colleague at the Hutch. So yeah, this is the paper if you're interested. Okay, so here is a simple motivation. Okay, so if you go all the way back to Angus Deaton's critiques, so people typically agree, I think, that the complier average treatment effect framework is elegant. Non-parametric identification, no more assumptions. This is elegant. However, it is unclear if this treatment effect among compliers actually generalize to bigger or the entire study population, because you can reasonably argue that compliers are very specific people, right? People are compliers maybe for a good reason. Okay, so it's not clear if the treatment effect can generalize the entire population. So one strand of work, they essentially propose so-called identification assumptions that tell us when the treatment effect among the compliers equals the treatment effect among everyone. So these are many different assumptions proposed by Jamie, Robbins, Eric, Sting, Wang. Limbo is actually an alumni from this department, and also Chris Wegener. So there are many assumptions that can link the treatment effect among compliers to essentially everyone. Okay. But this is not the most satisfying, right? Yeah, but because at the end of the day, you're still estimating the same estimator is presented. We are just changing the way to say what it is, and it has different interpretation. It's good to know what interpretation it has, but it's just the same number. Okay, so here is some intuition from essentially my discussion with Inchi the other day. So let's say you consider there's a randomized trial. Nowadays, the RCTs are typically multi-center. So let's say you run RCT at two clinical sites, one in Seattle, one in Portland. I choose Seattle and Portland because they're close to each other. So there's a little bit randomness in which site the person may enroll. So let's say Seattle versus Portland. Let's say the compliance rate in Seattle is 50%. The compliance rate in Portland is 100%. Look at the intention to treat, okay? So the effect of the IV, the randomizer on the outcome, let's say in Seattle, it's 2%. So let's say the mortality 4% in the treated group, 6% in the control group. You say, okay, there's a 2% intention to treat, okay? And actually, if you divide it by the compliance rate, it will give you the so-called complier effect. It's about 4%. So let's say, suppose the actual treatment effect is genuinely homogeneous. It's generalizable to everyone, okay? What would you expect to be the intention to treat effect in Portland? You would expect it to be roughly 4%, right? 6% in the control group, let's say 2% in the treated group, okay? Like this clear. So essentially, because in Seattle, only complier, the 50% complier contributes some treatment effect. If you believe the treatment effect generalized to everyone, then everyone would contribute treatment effect in Portland. And then the intention to treat would increase from 2% to 4%. That's sort of the intuition, okay? Let's say in reality, what you observe is the intention to treat is 2.2% in Portland. Okay, it's 3.8 versus 6%. Then I think intuitively, for me, this is evidence against effect generalizability. Okay, so there are more people who become compliers, but there is not a proportional, not even close increase in the intention to treat effect. So yeah, that tells you something about those additional people who are converted to compliers, right? Presumably the treatment has no effect for these particular people. So that's sort of the like, quote unquote intuition. I'll give you two examples where we actually have a natural experiment with a naturally strengthened instrument. So this is the example that Inchi told me the other day. That motivates the entire thing. So they run this PLCO trial, a cancer screening trial. So it's a clinical trial with non-compliance. So people are randomized to cancer screening, no cancer screening, but you don't have to take cancer screening. It's colonoscopy. So a lot of people actually opt out of colonoscopy. They don't want to take colonoscopy. So there are three centers, study centers. They initially adopted a dual consent process before 1997, but later they switched to a single consent process. Essentially, the difference is for the dual consent process, they ask the person one more time before colonoscopy, do you still want to take colonoscopy? And a lot of people actually just opted out. People just, they agreed to be randomized, and then they realize they are randomized to a treatment group, and they just bail out. They don't want to take the treatment. And then later they switched to a single consent. Surprisingly, you can still drop out, but actually just people seem to, for one reason or another, they actually, after you switch to a single consent, you don't give them one more chance to bail out. They actually, more people actually take the treatment. But of course, there are some other reasons maybe as well. But anyway, what the people actually found is the compliance rate in Henry Ford Health System, it actually improved from 50% before 1997 to more than like 90% after 1997. And in this paper, they're also very curious about this thing, and they found the single versus dual consent process actually resulted in a much higher compliance rate, even after they adjust for many baseline cohorts. Even for similar people, just by changing the way you consent people, they actually can increase the compliance rate. And for us, the most important thing for us is there is a valid instrument variable randomized to treat or control before 1997, and there is a valid IV randomized to treat or control after 1997. For me, these are two different versions of instrumental variable, and we want to do something with it. And here is a very recent example. So again, this is a paper published in the journal Political Economy. They want to study fat heterogeneity in what they call the so-called quantity and quality trade-off. Essentially, they want to study if there is any effect of the number of kids they have in the family versus their future development, okay? And economists are very good at instrumental variable. The IV they use is twinning. So essentially, if the second birth is a twin or not. And then treatment is the number of kids, 2 versus at least 3. If you have a twin in your second delivery, you would have at least 3 kids. If you don't have a twin, you would have 2, but presumably you can have 3 if you want, right? So this twinning at second birth, which is, most people agree, twinning is mostly random. It is associated with the number of kids, okay? And they use this as an instrumental variable. And what they found is, and a particular structure in the problem is they studied the birth control policy in China. And there was a period of time where they don't have any birth control policy. And there was a period of time where we have a birth control policy. And it's not too surprising, twinning is a stronger instrument for the number of children after the birth control policy was implemented. So again, this creates a natural strengthened instrumental variable, similar to the previous example. Okay, so we want to formalize it. So here, the intuition is if an encouragement is strengthened, more people would comply. I think that is sort of the intuition. And here, the key is we define 2 versions of a binary IV. So usually we just do 0 and 1, indicating a binary IV, randomized to treat or control. Here, I use subscript A and B to denote the version of this binary IV. So for instance, this 0A, 1A, it denotes randomization to control treat during the dual consent process. Okay? 0B, 1B is denote the same thing, but during the single consent process. And similarly, 0A, 1A is twinning or not before the birth control policy. And 0B, 1B is the same thing, but after the birth control policy. Okay. And we are going to make essentially a key assumption here, what I call a nested IV assumption. So that's assuming there's an identification assumption. If a person is a complier under one version of this IV, then the person would remain a complier under a stronger version of IV. Okay. So if you are a complier under 0A, 1A, you remain a complier under 0B and 1B. Importantly, we do not say anything about any other people. So you can be a never taker that get converted to a complier, which is fine. You can be an always taker, gets converted to complier, which is fine. You can be a never taker that remain a never taker, which is also fine. You can do whatever you want, but if you comply under a weaker version of IV, we believe you remain a complier under a stronger version of IV. So that's the key so-called nested IV assumption. Okay, now I'll tell you what I want to estimate. So so mathematically what we're saying is if D0A equals 0, D1A equals 1, so this is a complier on the weak IV, it automatically implies the compliance structure on the stronger IV. And you can imagine it's a reasonable assumption. And another assumption we made, which is I think even weaker, we just assume monotonicity for each IV, okay, for each IV pair. So for this first IV pair, we assume monotonicity. For the second IV pair, we assume monotonicity. So essentially, there are no defiers within each IV pair. Okay, so why do we bother this? Because under this partial monotonicity and the nested IV assumption, it starts to put some structure on this particular tuple. So this tuple is defined with respect to, for the same person, but under 4 different IV assignments. Okay, so this is if the person would, for instance, take cancer screening, if the person was randomized to control before 1997, randomized to treatment before 1997, randomized to control after 1997, randomized to treatment after 1997. Again, just like you only observe these 2 things, one out of these 2 things in a usual IV setting, you only observe 1 out of these 4. Okay, so the other 3 are conceptual constructs. Okay. Okay, so under these partial monotonicity and nested IV assumptions, you can enumerate all 16 possible principal strata, and only 6 actually remains. Okay, so most of them are not important to us. They're all, for instance, the first ANT is always never taker, They are never taker regardless of whatever. And we are particularly interested in this boldface switchers and always compliers. Okay, so here switchers are people who are non-complier will become a complier after we switch to a stronger instrument. And always compliers is just they are always comply. They even comply under the weak IV, essentially. Okay. And lastly, there is an assumption called mean exchangeability. So we create an indicator G. This indicates essentially the time period or study center. For instance, G equal to A means the person enrolled during a dual consent process. B, single consent. Another example is A. G equals to A if a person enrolled in Portland. B if the person enrolled in Seattle, etc. So this G corresponds to a particular version of this ID pair. Okay, so A, G equals to A corresponds to 0A1. GB equals to 0B1B. So this is important because at the end of the day, we are making inference based on the data, but for the entire population, at least the usual statistical framework. And here, these are usually referred to as a mean exchangeability assumption. So all they're saying is, you see, on the right-hand side, you have a population quantity. On the left-hand side, it's conditioning on the trial you actually participated. So the assumption is essentially saying the trial participation itself cannot modify the treatment effect, which is, it may not be true, but it's almost a minimal assumption, because if the trial participation actually modifies the treatment effect, then you can never learn what happens to the entire population based on clinical trial, right? So we'll have to take this mean exchangeability assumption. Okay, so anyway, I'll just define the two subpopulations of interest and the estimate. The first quantity I'm interested in is this, what we call it's a conditional always complier average treatment effect. So, and there is an associated always complier average treatment effect. So essentially, this is the per protocol effect, the effect of treatment on the outcome, but within this always complier subgroup. Okay, and analogously, we also have a switcher average treatment effect. So these are the treatment effect among the switcher population. Okay, so that's essentially a key, the thing that we are interested in. As sort of I try to allude it to. So if I know what is the treatment effect among these switchers, I sort of know whether or not improving the compliance delivers things that you actually want. Because there are people who do implementation science, and the one thing that I usually hear is people believe if I improve the compliance rate, I could improve the treatment effect or in ITT of this trial, which may or may not be true. It depends on people who are actually essentially depends on the treatment effect among these switchers. If eventually I do not detect any effect among switchers, that's essentially saying improving the compliance rate does not really improve the intention to treat because there's no treatment effect among the switchers. Okay, here's a simple illustration. So the entire population, there are a bunch of people who are compliers to this intervention on the Z1, a weaker IV, and there is a big population who are compliers under the stronger IV. And this is a simple illustration, but on the right-hand side, under the monotonicity assumption and nested IV assumption, so these people complier on the stronger IV, you can further decompose them into always compliers and what we call switchers. Okay, and what we are interested in, I want to make inference for these people's treatment effect. I also want to make inference for these people's treatment effect, essentially. Yeah. Okay. And this is what we refer to as a principal strata effects. And there are people who don't like principal stratification. And to them, I need to argue why we still need to, why this is still a meaningful thing. So the first thing is, I would say the switcher and always comply, there are meaningful subgroups. And even more importantly, later I will show we can actually tell you what is the distribution of these people's observed characteristics. So the typical critique is, for instance, for any single person, you cannot tell if the person is a complier or not, right? Because you only observe one out of the two potential outcomes. However, we actually can characterize the distribution of the observed cohorts for these subgroups. So we have a rough sense of who these people are, okay? And also we use it as a tool. Because again, go back to the generalizability problem, we can test whether or not the switchers effect equals the effect among the always compliers, or some version of them. So I also use that to test if the treatment effect actually generalizes. Okay. And sometimes we can also characterize the effect heterogeneity and establish what we call like an effect gradient. Okay. I'll just tell you, it turns out under essentially the nested IV assumption and partial monotonicity, we can identify the treatment effect among the switchers and among the always compliers. Here is the identification formula. So what it involves is essentially it's difference in difference divided by difference in difference, which is, again, intuitively, it's not that, it's pretty intuitive, right? What's the effect among the switchers? So you look at what's the increase in the intention to treat effect divided by the increase in the compliance rate. They give you it will give you the treatment effect among the switchers. So this is what we refer to as identification formula. And also, we can also characterize what's the average or whatever moment you want for the observed covariates within the switcher population and always comply population. These are all identified. I'll give you an example in the PLCO trial. So these are characteristics we estimated for the always complier and the switchers. One thing you do notice is for the switchers, for the always complier and switchers, they're actually pretty similar. And the switchers are more likely to be female, white, and they have a small BMI. So yes, and actually I just asked ChatGPT, typically people do believe female people with smaller BMI, they're actually at a lower risk, very low risk of colorectal cancer. And this sort of, at least to some extent, explains why we do not see a treatment effect among the switchers, because these switchers have very, very low colorectal cancer risk to start with. There's not much to reduce, essentially. But anyway, I just want to show you, we can actually characterize who these switchers and always complies are using this formula, okay? Yes, in terms of estimation, this is statistical functional. We can derive its efficient influence functions. Everything is EIF-based. It's a very long thing. It's a efficient influence function. As you can see, it involves many nuisance parameters, but you just need to estimate these nuisance parameters. And based on this EIF, you can construct the usual one step, or you can do an estimating equation. And there's also some details on the convergence rates. The one thing is you do need to, if you use an estimating equation-based estimator, you need to use standard cross-fitting, and you need to estimate a bunch of nuisance functions. There are probably 5 to 6 nuisance functions I need to estimate. And this is the rate conditions on the convergence rate for these nuisance functions in order for the resulting estimate to be asymptotic linear. If you're familiar with the literature, there's nothing too surprising. It essentially requires a quarter rate for these nuisance functions. This is the standard result, which is good. You see something standard in the literature. And I'll show you this is essentially the sampling distribution for the switcher effect. The ground truth is superimposed. It's pretty nice, asymptotically linear, asymptotically normal. And the data generation process is actually very complicated. There is no simple parametric function for any of those nuisance functions. So throughout, we just throw some black box machine learning tools, but it's okay. I don't care about, in some sense, I don't care about these nuisance functions. I only care about my target parameter. And the target parameter is nice. And the rule of thumb is if the sample size times the proportion of the switchers is at least 500, the inference is pretty accurate. Okay, I'll just lastly show you a little bit of results. So for this particular data set, we did estimate there is a hint of treatment effect for the always compliers, the confidence interval, but still technically it's larger than 0. There's a hint of effect for the always compliers, but we don't see any treatment effect for the switchers. Actually, the point estimate is positive. There's no evidence that the colorectal cancer screening has any effect on these switchers. Again, back to this intuition. Actually, the ITT pre-1997 is negative 0.26. So there's a hint of a treatment effect, reduce the mortality a little bit. It's a cancer incidence a little bit, and the ITT post-1997 is actually even smaller. It trended towards null. So, we did not actually, and the compliance rate actually increased from 50 to 80%. So we did not actually see the ITT increased with the compliance rate, which sort of explains why the switcher has no effect. And these switchers tend to be female, white, small BMI. This population has very low colorectal cancer risk to start with. It's a reasonable, well-rounded story. It's a reasonable result. Okay, so a brief summary. Just if you have some take-home message from this talk, we don't have to accept an instrumental variable as it is. The switcher treatment effect is useful for researchers, for instance, implementation scientists. They study actually ways to improve the treatment adherence. And also it is useful to identify and leverage factors that may modify the compliance rate, which is, I think, underutilized. Yeah, and actually, as a small generalization, we also wrote a paper more recently where we can also develop design-based methods that avoids all the superpopulation or the influence function. You can just use randomization to estimate the same sample average treatment effect among the always compliance and among the switches. Okay, cool. That's it. Thank you very much.
So we have a few minutes for questions.
You mentioned that this is useful to identify the compliance rate, but not all, right? Like when it's the same instrument that has been, I guess, like followed, like basically, like there is no quantifiable definition of strengthening an instrument for if it's a binary. So like other factors that can modify the compliance rate would have like other, like there'd be other variables in the DAG. So this is accounting only for like when you have strengthened the instrument you already.
Yeah, I think what I'm trying to say is, sometimes you can pre-plan some subgroup analysis where you can still study, for instance, you can bound the treatment effect or study effect ratio, for instance, among like Black mothers or among the non-Black mothers, where the compliance rate could potentially be different among different subpopulations. But of course, you have an average compliance rate if you study an average over X, right? It depends on what things you are actually average over.
So this may be a bit of a silly question, but so your outcomes here are absolute effects, right? So difference in proportions. If you were to look with relative risks instead of absolute risk, right? So difference of log odds, if you will. Is there anything that changes? Because one of the things that you mentioned is, for one of the studies, one of the reasons why you don't find the effect is because, the baseline effect is very low.
Yeah, that's true.
But if you look at it in terms of relative risks,
That's
that
no point.
dynamics change.
Yeah, that's a good question. I think, that's a good question. It's possible because even if at this RD risk difference ratio scale, if there is little difference at the risk relative risk scale, there may be a difference. Actually, this is a good question. We can, I think the inference should still be proceeded. We can still do inference for the relative risk, and we can probably see. And this is a good question. Actually, the fundamental question is, in most of those assumptions, if you look at those assumptions, yeah, there are a lot of details. If you look at these, assumptions, sorry, sorry. So yeah, if you look at these assumptions, a lot of these assumptions are scale specific. They actually work for the risk difference. Or if you work with a relative risk, odds ratio, or whatever other effects measure, they need to come up with a different assumption in order to justify these, in order to do these things. And yeah, I'm absolutely right. We can see if I don't know if the inference is that straightforward, but that's a good point.
Okay, no, thank you everybody, and thank you.